It is now 6 o'clock, so time to get started. Tonight is dedicated to reviewing for the final exam. So let me show you what's on Blackboard to help with that. And also, it might be helpful even tonight if you haven't had opportunity yet to construct some questions for the review. If you look through that, what's on Blackboard, it might remind you of something that that you would like to ask about. So if I find the right button here, there we go. Get this screen shared. Let's see. All right, I think that's working for me. Hope it's working for you. All right, there is actually an announcement on it, but basically it says look in the week 14 folder, which is where we are here. And there's a little bit of general information about the exam. The exam will be done pretty much like the previous ones in this class. A lot of instructors will hold exams. Oh, that's hard to see, isn't it? Let me magnify it. Better? Okay, a lot of instructors will hold regular exams to 1 hour. So during the regular part of the course, if you take an exam, it's just a 1 hour exam, and then your final is twice as long as the others. I have found that to be pedagogically a bad move because if you give a lesson before the exam, everybody's so worried about the exam, they don't think about what you're teaching. And then if you like to give the exam, take a quick break, and then do a lecture, everybody's so tired, they're also not listening. So I usually just do 2 hours for the exam. And that means that all the exams are the same length. So you should expect the final exam to be about the same number of questions, about the same amount of time to work as the other 2. As last time, I will be here at 5:30 and I will stay till 8:30. And I'm doing that for multiple reasons, but I have had some people share with me that, you know, they work out of town and honestly, they just cannot get here by 5 o'clock or rather by 6 o'clock. So they appreciate having the time run over a little bit at the end. There's other people that need to leave early. There are people who find that, you know, they just feel like they tend to work a little slower than some other people, and they just would like to have some extra time. And there are people who don't need the extra time, but they're glad for it because it makes them less nervous. And I don't care which of those categories you fall into. You're welcome to come start the exam up to 30 minutes early, and you're welcome to stay 30 minutes late, and you can do both if you want. And no, you don't have to tell me ahead of time. And no, you don't have to tell me why. Just do it and it'll be fine. Because I'm going to be here, so I won't care. Unlike the other 2 exams, this one has a feature that is different. You may bring one 8.5 by 11 sheet of paper. So normal notebook paper size. Let's see if I can get my camera working there. And you can write on just one side of it. And some people in the past have asked me things like, well, could I cut it in half and write on both sides? Yes, you could. You could cut it in quarters and write on both sides of one piece. Let's see, that'll give you 1 quarter. And only one side of 2 other pieces. So that would give you another half, right? And then make up the difference on the last one. So I don't care, so long as the area on which you are writing does not exceed 8.5 by 11 inches, it will be fine. I also usually, when I do this, I get questions like, well, could I put formulas on there? Yes. Could I put example problems on there? Yes. And after a while, I say, look, there's no restriction on what you put on there. If having a picture of your mother on there helps calm you and makes you do better on the exam, then by all means, print a picture of your mother on your note paper. I don't care. Now, it should be, anything that you put on there should be appropriate for polite company. But other than that, there's no restriction. The restriction is the amount of space you have, not what you can write on there. So for instance, if it were me, if I hadn't been doing this for years, if it were my first time, I probably would have some Laplace transforms on there. Why? Just because, there's a list of them and it'd be easy to get them mucked up, and that would be too bad if you did a problem perfectly, except that you had the wrong formula. So those sort of things are welcome. And I think last time I gave you a formula for an integrating factor. I won't be doing that this time, but if you want it, you've got plenty of room to write that on your paper. Okay, so feel free on that. The first part of the exam will, however, be no notes and no technology. It's brief. Like in the past, it's been 1 page for the first exam, right? So it'd be something like that. Might spill over more than 1 page, but it wouldn't be more than 2. And they're just quick questions that I'm probing to find out if you have basic information stored and whether you can do, very basic calculations without the aid of a calculator. So when you come in the room for the exam, it'll go like this. You come up to the front, you leave your note sheet at the front with me. You take both parts of the exam back to your seat, you start work, and you are welcome to use your calculator or to come up and get your note sheet anytime after you turn in the first part. So the first part has to be done without those aids, but the rest of it's fine. There are some notes on this topic outline that tell you, give you some hints. So for instance, here's some stuff on matrix arithmetic you should be able to do without the aid of a calculator. And then I mentioned a couple of other things you should know if you want to be, fully prepared for that section to work without a calculator or notes. Namely, there's a few infinite series I would like you to commit to memory. You should know Euler's formula. E to the I theta is cos theta plus I sine theta. And you should know a handful of things about Laplace transforms. Now, if you forget one, it won't be the end of the world. There's, not only so many points I can put on a question, but those are the things I'm asking you to have committed to memory. So how do you take the Laplace transform of 1t, t to the n, sine theta, cosine theta, e to the I theta, and then that formula in terms of the integral? So you should know that. Okay, is that clear, Sam? I see you squinting. Is that? We're good. Okay. And I think that's about it for the no notes part. And the rest of this is just a outline of what we've done. To tell you the truth, I made this outline 2 years ago, the last time I taught the course, and I got it out last night and updated a little bit because we did some things slightly differently. Not everything in this outline is of equal importance. So, there are some things on here that are kind of minor-ish things, like for instance, that is Bessel's differential equation. And you should be able to recognize it and you should be able to write down the solutions for it. But that's it. You know, I don't expect you to be able to evaluate Bessel functions because we just have not really talked about them. The only reason I'm asking you to do this is to sort of emphasize the fact there are a few of these special equations of mathematical physics that you're almost certain to encounter some of these in your future career. Whether it'll be Bessel's equation, I don't know. But it's good to know that there are famous equations that have been worked out in detail, and you know, you can simply look up the solutions for them, and there's computer code to evaluate them and things like that. So with that introduction, I think I will stop talking about this. I am happy to page through this as we go on tonight, but I think what I'll do, since I announced ahead of time I was going to ask for questions, I'll pause for questions, and then when I get to the end of those, if we've got time left, then I'll display a page of this review, and you can look at it for a minute and see if there's anything you want to ask about. When we're done with that page, we'll go to the next one, etc. I think there's a total of 3 pages. 4. Well, good. We'd hate to run out. Okay, so and of course, if you got if you're joining us online or you have a computer or a phone with you, you're welcome to pull that document up as we work tonight. All right, so oh, but by the way, I will also be trying to check in occasionally on the chat box, and I see I've got one thing on here. So I'll be looking at this occasionally to try to get questions that way. If I'm missing you and you put something there and I'm not responding, well, after an appropriate amount of time, you know, just say something and I'll read it. Okay. One question on the note sheet is this: can it be typed or does it need to be handwritten? The answer is there's absolutely no restriction on what's on there. If you have the capacity to create a 400-page document and store it on something like microfilm, and then put some little nano devices on your glasses and you can point your glasses at it and read page after page, that's fine. If it fits on an 8.5 by 11 piece of paper, it's legal, okay? Except, as I said, you know, like it shouldn't be pornographic or something. Nothing that would get you in trouble in general at GRCC should be on the page. But otherwise, mathematically, there are no restrictions. So typing is fine. Graphics are fine. Okay, does anybody have a question they'd like to pose?
Could you go over inner products just a little bit? I vaguely recall that it's like dot product, but wasn't there a little more to it than that?
Thanks. All right, the question is this: could I go over inner products, and is there anything more to that? It's not, I'm rephrasing here. Is there anything more to that than just plain old dot product? The short answer is, practically speaking for this course, no. The only inner products we really worked with to an extent were just the plain old dot product from calculus. Now, are there other inner products? Yes, there are. And you can create them with matrices. You can also create them with integrals. But, you know, I hate to spin down into a long discussion about something that realistically is not going to show up on the exam. I have to stick to major points for the final exam, and that's not one of them.
Okay.
Any others?
Will we have to do anything with numerical solutions other than?
Yeah, let me share my screen here because I can answer the question a little better. If you didn't get that, the question is, will we have to do anything with numerical solutions of ODEs? And I think the best way to answer that would be for me to scroll down here to this document where it's listed. And I'll tell you what I meant by what I said. There are things I could ask about. So for instance, big O notation is one. It's used primarily, well, for us, I think it was used exclusively for talking about the order of the error bound on methods for solving problems numerically, either ODEs or interpolation with cubic splines. There's some basic facts listed here for Runge-Kutta method. So, you know, you should know these, but I mean, that's pretty much all there is to know is what's on there. You know, if you, and the idea of behind an adaptive method, and then the idea of why do we use a cubic spline? Well, I pretty much put the answer there. Now, would I ask you to say compute by hand a cubic spline, or to compute, apply the Runge-Kutta method on 4 steps by hand? It's just not practical. It's just too hard. Years ago, we used to do some stuff like that. We'd get students to write code way back, it'd be like Fortran. And they would run some code. But nowadays, with systems like MATLAB out there, MATLAB is probably the big player. It's just for basic application of those algorithms, there's really no reason to code your own. They're better on MATLAB than you're going to make them by hand. and I don't mean just you. They're better than I would make them, because they're typically they draw on research from world experts. So they're as good as they get. Let me mention just a little bit about big O notation, because that is something that I'm frequently asked about. Okay. Big O notation, we usually write something like this. First of all, if you're doing a numerical method, the idea is you've got some interval from A to B, and you cut this thing up into pieces so that when you're trying to find solutions to, say, an ODE, you're stepping along the t-axis or the x-axis. That distance between adjacent stopping points is usually referred to as h, and that's the step size. So if I say something like this, the error is big O of h to the 4th. And by the way, that's the truth for both a cubic spline and for the standard Runge-Kutta 4th order method. What it means is this, that the absolute value of the error is bounded by some constant, and this is where it gets a little bit slippery. You know, what constant? Well, we don't know, but there is a constant. And this error will be less than or equal to the constant times h to the fourth power. Now, in practice, we're usually thinking of h as being something close to 0 but positive. So, for instance, this is not a very small one, but 0.1 might, that's a realistic size for a step size you might be working with. And what we're saying is that the error is then bounded by k times, that's 1/10 to the fourth power, or k over 10 to the fourth. Now, at first sight, it would be easy to dismiss this and think, well, that's a vacuous statement. Every finite number is less than k over 10 to the fourth. You just make k big enough. That's true, but here's the thing that the big O statement tells us that we wouldn't have without it. And that is, let's suppose I started with h, but then I decided, I'm getting too much error. So I'm going to take a smaller step size, let's say h over 2. Well, big O of h, that we're thinking is approximately, it doesn't make any sense to use to say this is order of h squared when it's really h to the fourth is also true. You want that power to be as high as possible. So we're thinking of this as there's some constant, and once you get going, eventually this will be about the size of some constant times h to the fourth. Well, what happens if you cut your step size in half? Well, the answer is you've cut your error bound by a factor of 16. You had this error bound for your first step size, you cut it in half, and now you've got only 1/16 of that. So that's really where this is useful. It tells us how quickly that error bound collapses. What we'd like is the error bound to be 0. We'd like perfection, but you can't have it with numerical methods. So saying that it has fourth order tells me, well, if I cut my step size in half, I'm expecting about 1/16 of the error that I had before. So that's good. And you can see, let's try that with error bound that's say big O of h squared. Big O of h squared, for h, we're saying the error is about kh squared. What happens when you replace that h by h over 2? Well, it's k times h squared over 2 squared, 1/4 of the previous error bound. So a second order method is nowhere near as good as a fourth order method. Cutting the step size in half on a fourth order means we're expecting error to decline by a factor of about 16. Cutting the step size in half on a second order method means we're expecting the error to decline by a factor of 4. So, so there are some practical questions at that point that I could ask. Suppose we're doing the Runge-Kutta method of order 4. If we cut our step size in half, what do we expect to happen to the error? There is one that you weren't told. It was a method for solving differential equations numerically, but in fact it is. You learned what's known as Euler's method in calculus, and the instructor sooner or later is going to get around to this. They say, okay, we draw the tangent line here, and if we just made our x go over a little bit, then we could follow the line instead of the curve. And that's called linearizing your function. And it's actually useful. It's an important idea. but numerically, it's useless. It doesn't work very well. If you follow this broken line kind of estimate, that's known as Euler's method. Over the whole interval, it's big O of H, which is to say, it's awful. You can code this up and you will get an estimate, but I'm trying to draw generally what happens. The computed solutions tend to diverge from the real solution very rapidly. It's big O of H squared in a single step. It's big O of H over a whole interval. And same thing goes for Runge-Kutta. It's big O of H to the fifth on a single step, but over an interval, it's big O of H to the fourth, which is excellent. And cubic splines are big O of H to the fourth, which is another reason we use them to interpolate the dots on the plane we compute for solving ODEs. So that's about covering the whole course worth of stuff right there. Does that answer the question?
Yeah.
Okay. Well, in that case, why don't we, since questions are coming in slowly, let's just kind of work our way through here. Maybe it'd be better to, we've done this recently. Well, let's do this one because this is on people's minds just because you've worked on it recently. And then I'll jump back up to the beginning of the document or something. Anybody want to ask about any of these things on Laplace transforms? Linda? Yeah, computing using the table means something like this. Let me switch cameras so everybody gets to follow. Oops, that's not the one I want. The question was this: on the outline, it says solve problems essentially by using transforms from the table. And what that means is something like this. You have for instance, you have a formula on the table that tells you, I don't know, we'll just make something up here. Sinh, I mean, I'm picking something at random, not this is a real formula, I'm not inventing it. Sinh of AT has transform S over S squared minus A squared. Oops, A over S squared minus A squared. And let's suppose then that in your differential equation, you got a bunch of terms here, and the right-hand side is set equal to the sinh of 3t. Well, use this formula to find the transform of that. Okay, so it means be able to use the formulas to your advantage. Or another thing it could mean would be even to be able to combine them. So there's another formula that says this: e to the at f at t, little f at t, has transform cap f at s minus a. So if your equation ended this way, e to the 5t sinh of 3t, then the transform of this function here must be well, to transform e to the 3t, you'll go to this. And if you sinh of 3t, you'll go to this, and then you toss on the e to the 5t, it just puts a shift on it. So that will be in the denominator. You'll get s minus 5 squared minus a squared, which is 3 squared. So there it is. So I'm able to apply these formulas in order to get my transforms or inverse transforms, which is a different kind of a problem from saying, show me why the transform of 1 is 1 over s. Because on that one, you already know the answer. It's filling in the middle, right? So in that case, you get out the integral and you do the integration and you'll get 1 over s.
Is there going to be much of that? Doing the integration for the Laplace transforms?
No, and I have two answers to that. The question is, will there be a lot of deriving formulas from the definition of transform? Frankly, there can't be a lot of anything. If you look at the length of this outline, there's a lot of stuff in there. And I get about as many questions as I usually do for a test. So I can't dwell on any one thing. Now, maybe another question would be, do I think this would be, prove this statement? Do I think that's a reasonable question for a final exam? Yes, I do. On the other hand, there are some things I would not ask you to do. And they have to do with like solving equations where, you know, it just turns into a nightmare of algebra. You have maybe 2 pages of calculations and you end up with an answer like sine of 4t plus 3. Oh, good grief. I could have done that so much faster another way. Yeah. So I will endeavor to avoid those. Okay, let's are we good on Laplace transform? Does anybody want to ask a question about that? Or should we move on?
Maybe on, there was a problem from the homework that implied some partial fraction decomposition, and it ended up being a fairly big matrix to solve to get all the coefficients, at least in my case. So I was wondering if there was a quicker way to solve it.
Yeah, I think to restate the question briefly, it would be this. Some of the partial fraction decompositions are really tedious. They take a really long time. Is there any way to speed it up? And the answer is sometimes there is, but not always. For instance, let me switch cameras here. If I had something like this, so there's my Laplace transform, and I would like to find the inverse transform. And the natural way to do is to split this up. Well, there are 2 approaches. One approach is to say, well, I could have something of this form. Technically, you could have that as well. And then that. And then that. Oh, good grief. 5 variables, and you know, when I work with it enough, eventually I'll come up with 5 equations or some way of determining these. In principle, this is not hard, but in practice, it is, because you know, little mistakes will just kill the calculation. So there's another thing you could do, and that would be to say, well, what I could do is split this then that will get me back to some f at t. And then I have a theorem that says you can handle these factors of s by integration. So I would take this, integrate once, to take care of one of these factors of s. And then having done that, that will give me a function of t. Then I'll integrate again. Well, I don't know what to write here. I've used up x, t, y. Well, that's a bad idea. R. And that would give me a function. So I could do it this way and then integrate twice. In practice, you don't have to write all this fancy stuff. You integrate from 0 to t twice. So in that case, you can speed it up, but it does come at a cost. You know, you've really reduced the complexity of your partial fraction calculation, but now you got to do 2 integrals. And that may or may not be easy. In this case, it is easy because you get exponential functions here. I think we could probably split this by guess and check. If I did say 1 and minus 1, it would almost work. I get a 2. So it's a half and minus a half. I think. If not, it's something really close. And then when you take the inverse transform of that, you end up with 1/2 e to the 3t minus 1/2 e to the minus t. So you integrate this on the interval from, you know, you change the t's to x's, integrate from 0 to t. And you'll get something, it'll be exponential. And having done that, let's give this a name, g at t. And having done that, then you integrate once more. And that thing will be your inverse transform. So in this case, it would be practical. But, you know, there are some problems that are just horrific no matter how you do them. And in practice, what do? Try Wolfram alpha. That has solved some of my worst algebra nightmares. And I think, why not? We know how to do basic algebra. It's the 6-pagers that give us trouble. So why not let a machine do that? Okay, well, let's go back to the list. Anyone else want to ask anything about Laplace transforms before we move on? I'm not sure I can see my chat. Well, I am sure. I can't see the chat without switching out of here. So let me just check in. Oh, I do have a couple things here. Around how many questions will there be in total? Look at your previous 2 exams and see what it was. It'll be about that. I don't remember right offhand. I think I've been giving like around a dozen questions or so, but I will be judging that in the same way you would. You know, when I write a draft exam, it's always 100% of the time, it's way too long. And so then I look at, and then at this point now I have 2 previous exams to look back at. I'll go back and look at those and say, okay, well, how could I adjust this draft so that it would take about the same amount of time? So the answer is, I think around a dozen questions or so, but look at your other exams, that will help you out. And by the way, I think I might have posted the keys for the other exams, didn't I? On Blackboard?
I think so.
But if not, they're certainly there by means of video. The next question is, what is the ratio of new material to material that was covered on previous tests? Probably about half and half. I probably will put, if I were to make it, if we had a third unit exam and then we had a final, I would make it a third, and a third from the, the 3 sections of the course. Since we don't do that, I probably will devote about half of the exam to the new material. But as you know, that's multiple topics. That's power series methods, systems of equations, what else? Laplace transforms and numerical methods. So saying half of the exam is going to be covering those 4 topics. There's not many questions about any one thing. Okay, well, let's go back to the list then. Series solutions. There are some basic series you should know. E to the x, sine of x, cosine of x, and 1 over 1 minus x are really important.
For the amount of questions, does that, when you say it doesn't, does that apply to both the no technology part and?
No, the no technology part might have a half a dozen things on it, but they'll be really short. I do not want to put something on there where you're going to be bogged down. You answer it and move on. And especially if it's something like asking you for a formula. Tell me the series for sine. If you look on the list back at the top of this sheet, it says you should be prepared for that. So you just write it down, you move on. Or here's a I don't know, how about a 2 by 3 matrix and a 3 vector. Multiply them. Okay, you just do it, So no, that wouldn't include that count. But the first exam had that style, so you have an idea. We had techniques for finding new series from old ones. Basically, substitution, differentiation, and integration. That's pretty much what we did. And then, of course, you can do things like, if you can get the series for sine, then sine of x, then you can get the series for x squared sine of x. You just bump all the powers of x up by 2. So there's little tricks like that, but there's not much we can do. One thing I should point out about series solutions is these tend to be longish to do one of these problems. So the question is, could I even ask anything? And the answer is yes. What I can do is ask a part of a question. So I can do something like write down a differential equation and say, follow the method of solution by infinite series up to the point of getting a recurrence relation. Once you get the recurrence relation, you stop. Well, that's cutting a lot off. So, or I could give you a recurrence relation and say, find the series solutions. Or I could give you a couple of series, and I put one in here as an example. Suppose I give you that one and say, what function is that? Well, hopefully you would be able to look at that and say, oh, that looks a lot like the e to the x function, except I got these powers of 2, and then you say, oh, wait a minute, that's just x over 2 to the nth power. That must be e to the x over 2. So, and those are all part of what you do when you solve a equation by power series method, right? So I can ask for a little piece of that, and that's usually what I do. A whole one, I either have to make the problem so simple that it doesn't tell me anything when you solve it successfully, or it's too long, and it doesn't help me either, because what I found out is 3/4 of the people didn't finish it correctly. Why? Well, they dropped a minus sign somewhere, or a 2 turned into an x, or some stupid thing, which we all know better than doing, but we all do occasionally. That's not very revealing. The purpose of the exam is to find out if you know what parts of the material you're competent on and what parts you're not. So it's silly for me to ask questions that are either guaranteed that everybody will get them right, or that almost everyone will get them wrong. So that makes this a little bit delicate here. Okay, ready to move on? Let me stop the share so I can look at the chat box. I might have something new in there. Nope, I don't. Okay, let's look back at the previous section. Oh, systems of ODEs. The truth is, we didn't do a lot with that. What we did basically was this. You find the eigenvalues and eigenvectors for the matrix of the system, and then you use that to write down a solution. We also talked a very little bit about the phase plane portrait and critical points, but the primary use we made of that was in predator-prey systems. We solved them maybe numerically, and then we draw the phase portrait in that case is y1 versus y2, as opposed to if you have a single second order equation, oftentimes people will plot y versus y prime. In the case of predator-prey systems, we look for like a spiral solution where the solution will zoom into a point. Well, that's telling us there's this stable place where if you start anywhere near that, you're going to tend to get a population of predators and prey equal to that value. Sometimes you see something that looks sort of kind of like an ellipse, and that tells you, well, it never really stabilizes at one point, but it is more or less cyclical. So it tends to behave in this way. That's primarily what we use that for. And that's about what we did with systems. Had pretty limited time for that. Okay, let me check for text questions and then we'll move on. No new ones. Okay, next one back is the basic methods of solving first and second order ODEs. This is an area of the exam where you should really do well. And the reason is it's algorithmic. If you can remember the basic categories and algorithms, and you can do calculations, you should get these right. Now, I don't mean to negate the fact that we all make errors. Of course, that will happen, but you should generally know how to do all these. So if once you see the list, you begin to realize it's not that long. It took a long time to go through it the first time, but the truth is, if I'm going to write a first or second order equation, I don't have a lot of choices. They're going to fall into one of these categories. And then if I'm going to put a non-zero right-hand side on it, I'm really limited in the techniques I could ask about for finding the particular solution. There's only three. Well, there's always a fourth one, which is you stare at it and think, oh, I got it. It's x plus 3. Well, usually if you can do that, you could also have done one of the other methods. Okay, let me check back on the text. Nope, no question there. All right, so there's just one other section left, which takes a while to get through. It's kind of long. Linear algebra. So let's look at the first part. There's basic stuff. There's quite a bit that you can say about invertibility and determinants. The short answer is that a square matrix has a non-zero determinant if and only if it's invertible. But there's a whole string of things about number of solutions and stuff like that. So a linear system could have 0, 1, or infinitely many solutions. So all of that is worth being aware of. And this, CS means column space, NS means null space, RS means row space. The dimension of the column space and the row space are always the same. And if you take the dimension of the column space and add the dimension of the null space, you always get the number of columns in the matrix. And of course, if it's a square matrix, that would also be the number of rows. Okay. Linear transformations, and in particular change of basis, is something I often get asked about this time in the course. Is that all good, or does anybody need a refresher on how to do the change of basis?
Can you go over it again?
Yeah, let me, okay. So let's talk about change of basis briefly. What I'll try to do is give a concrete example that can be calculated fairly quickly. The standard basis for, say, R3 is this, which you all know. I don't pretend I'm informing you. I just want it written down. On the other hand, this set is also a perfectly good basis. It's not nearly so convenient. I'm sort of taking, if you think of zeros and ones, like trues and falses, I'm just going to take the opposite. So this one has a 1 and 2 zeros, so I'm going to make it a 0 and 2 ones. Likewise, I'm going to put a 0 in the middle and a 0 at the end. That's a perfectly good basis for R3. So both of these are bases for R3. Now, if I picked a vector in the normal notation we use, let's say we had the vector 2, 3, minus 1. What that means is those are its coordinates relative to the standard basis x, s. So it's 2 times, actually we have some standard names for these, I, J, and K, right? So it's 2 times I plus 3 times J minus 1 times K. So I can express this vector as a linear combination of those. Can I do it with this? The answer is yes. And there are basically 2 ways you can go about that. One way is you could simply solve a system of linear equations. You could say, okay, I've got this vector, I want to multiply by something, let's call it x1. Whoops, I wrote the wrong vector. Maybe I shouldn't call it x, because that could get confusing. I'm going to call it C to stand for coordinate. For coordinate 1, it would be something times this first vector plus something times this second vector plus something times this third vector. And it's supposed to add up to 2, 3, minus 1. So then if you look at this for a while, you realize, oh my goodness, that's a system of equations. And you put that in your calculator or whatever, and you solve it, and it tells you the coordinates in this system. That's one way. It's a good way if you have just a single one to do. It's not so good if you if you'd like to come up with a system that would allow you to translate a bunch of vectors. And sometimes you need to do that. So if you want to translate a bunch of vectors, what you do is you say, okay, I got my standard basis here, and we usually made a diagram of these things. And then I've got my A basis here, and let's say this is V1, V2, V3 for my vectors. And that we'll do that. That's good enough for now. Now, oh, sorry. Now, if I want to, if I had some coordinates, ABC, in the A basis, I could easily transform that to express the vector in the S matrix, S basis. What I would need to do is take A times the first vector plus B times the second vector plus C times the third vector, which is this. You take the first vector for the first column of the matrix, V2 for the second column, V3 for the third column, and multiply by ABC. So what we're saying is this. If you had a vector here, say X, with A coordinates, you could translate it to S coordinates by taking this X vector and multiplying it by the A matrix. It goes on the left. So multiplying by the A matrix will get you from A to S. And then to go the other way, you would do the obvious. I think before I wrote it this way, it is the matrix I compose by using these vectors V for the columns. So, so I actually had one in mind, right? I had 0, 1, 1, 1, 0, 1, and 1, 1, 0. So if I would like, and let's take a particular one here. 4, -1, 2. And these are coordinates in A. I would like to translate this to S. This is what I do. I start with the coordinates in A, and I multiply on the left by the matrix that is created out of this A, basis. Now that's good by itself, but it also tells me this. Okay, what if I had this? 3 - 4, 7 in the standard basis. How do I express this in terms of this non-standard basis? Well, the answer is you go backwards with A inverse. So then I would take 3 - 4, 7, and I'd multiply on the left by the inverse of this matrix. The last thing I could, and how do you do this? Well, you do it on your calculator, right? This is just way, way too much work to try to do by hand. Even though you might well be able to do it, there's a lot of symmetry in there. Likely it would clean up without too much difficulty. The other thing that I talked about in class was this. I said, okay, now let's suppose you have 2 non-standard bases, and you'd like to go between these. How do you do that? Well, the answer is you just imagine that you have the standard bases available, because in fact you do. And so if I started with an X with A coordinates, how would I write X with B coordinates? Well, the answer is first I would translate to S, and I would do it this way. X with A coordinates, multiply that on the left by the A matrix, and that will get you X. The result will be X with standard coordinates. Having done that, then I want to come down here to B. So now to go from S to B, I use the inverse. So I take my X in standard coordinates and multiply it on the left by the inverse of the B matrix. But of course, this XS is just this. So that's the B matrix inverse times the A matrix times the X vector with A coordinates will give you the X vector with B coordinates. And of course, that'd be a lot of calculating if you didn't have a calculator available. But for say a 3x3 and you got your TI calculator there, you could do it. Though likely on an exam, if you wrote it in terms like these, unless I said to compute it, that would be good enough. You'd say, well, this matrix inverse times this vector, you're done. Okay, that's good. Does that answer the question?
Yes, thank you.
Mm-hmm. Okay, let's click back here then. Change of basis, we talked about that. Linear independence and span. Would anybody like to ask a question about that or just ask for a general refresher?
Perhaps a general refresher of span might be nice.
Okay, the question
It
is,
what it sounds like.
yeah, could I just talk a little bit about the span of a set of vectors. And first of all, I suppose would be to know the definition, the span of, now let me give something a little more concrete. I could write this in general, but I won't. Suppose I had 3 vectors and I write down the span of that. What does it mean? It means the set of all linear combinations of V1, V2, and V3. And you can write that officially. It means this: every vector you can make in this way, some constant times V1 plus some constant times V2 plus some constant times V3. So there's a span. The span of a set of vectors, so let's call this set here, cap V. The span of any set of vectors is always a vector space in its own right, which is to say it's for the kind of vectors that we would be dealing with, it's going to be a subspace of Rn for some n. And the n will be obvious. If these are vectors with 3 entries, then it's a subspace of R3. Now, it doesn't automatically have dimension 3 because this could be linearly dependent set. So, but you do know, no matter what vectors with 3 components I write down here, if I take their span, I've got a subspace of R3, guaranteed. About the only other thing that comes to mind right now would be, you can always ask questions like this. Is this particular vector X, and I'll give an example here in a minute, is that in the span of this set of vectors V? So to be precise about that, let's give a definite example. Is 1, 2, 3 in, that means a member of, the span, an element of, that's where it comes from. The span of, and let's make up some vectors. Oh, and I'll try to make it obvious at least what part of is going on here. So is this a member of the span of that? Well, first of all, if these 3 were linearly independent, then they would have to span all of R3, and the answer would be yes, without any calculation, just because I would have all of R3 sitting here, and that certainly is in R3. But a quick observation will tell you, oh, look, if I add the first 2, I get the third one. So this is a linearly dependent set. So the span of these 3 is really the same as the span of the first 2. So can I get to 1, 2, 3 from that? Well, you could think on it a long time, or you could just let a calculator answer for you. You'd say, well, let's suppose I could. Then I'd have to be able to find 3 constants, C1, C2, and C3, or you could call them X1, X2, and X3 if you like, so that C1 times the first plus C2 times the second plus C3 times the third adds up to this. Which means you could put this matrix in your calculator and append this extra column to it, do the row reduced echelon form, and you know, you'll have the answer looking at you. If you get something that looks like this, and let me just put something that I'm quite certain is not the solution, but if it looked like this, then the answer is, oh yeah, 4, 5, and 6 will work, it's in the span. But if you get something that looks like this, and who knows what's up here, it doesn't make any difference. The answer is no, there is no solution. This is a contradiction. 0 times 0 times x1 plus 0 times x2 plus 0 times x3 is most certainly not equal to 2. So if you get this sort of thing, the answer is yes. If you get this sort of thing, the answer is no. But better than that, it's not just yes, it's yes and 4 times b1 plus 5 times b2 plus 6 times b3 is the desired vector, whatever that was. W, maybe. In linear algebra, about 90% of all things come down to row reducing a matrix. It's which matrix and how to interpret it. So?
Yeah, so you could say that, I guess I didn't know you could have linearly dependent spans.
Well,
Maybe I missed that.
the vectors we start with are linearly dependent.
Mhm.
And therefore, but we can still talk about the span of those vectors.
And if they're independent, then they are also a basis, right?
Yes, if you have the right count. These are vectors out of a 3-dimensional space. I have 3 of them. If they are linearly independent, or if they span the whole space, they're guaranteed to be a basis. Because there are these statements. The set is a basis. Two, the set is linearly independent. Three, the set spans the vector space, whatever vector space you're working in. Now this is, I should say, all of this is under the assumption that you have n vectors in an n-dimensional space. It turns out that if any 2 of these are true, the third one is forced to be true. So actually, this one is even better. If it's a basis, both of these are guaranteed to be true because that's the definition. But if you have n vectors in an n-dimensional space that are linearly independent, they're guaranteed to span the whole space. If you have n vectors in an n-dimensional space that span the whole space, they're guaranteed to be linearly independent. And of course, when you get those 2, then that's definition of basis. Okay? All right. All right, let's, where were we here? Linear independent span and basis. Oh, there's always these questions that ask, is this set a subspace or not? Does anybody need a refresher on that, or are we good to go?
Can you do a refresher on that?
Sure. Okay, a typical question would be something like this. Let me give you 2, actually, 2 examples. One where the answer is yes, and one for which the answer is no. So suppose I ask this. V, cap V, is the set of vectors to t minus t. And you could add some extra stuff here, but it means just what it looks like. Anything, so something that fits that pattern is 2, 1, minus 1. That's in this set. And likewise, 2 minus 1, 1 is in that set because you could take t to be minus 1, right? So everything of this form is that, I guess for English we do it this way, right? Is V a subspace of R3? And on this one, I can answer instantly, no. Why? The zero vector is not in the span. Well, that's sort of written as a span, is not in V. So, you know, I can't set that first component to be 0, so I can't get the zero vector, and therefore it's not a subspace. Another common way that you'll see quick answers would be something like this. How about, oh, let's see, I'll try to disguise what's going on a little bit. 2, 3t, I said 2, but I meant t. 3t, 7t, where t is greater than or equal to 0. Is W a subspace of R3? Answer instantly, no. And here's why. 1, 3, 7 is in W, but the negative of 1, 3, 7 is not in W. And that is the point of this statement on the review sheet. Let me get back there. A subspace always includes the zero vector, and if x is in the subspace, so is minus x. So those are two quick tests. If it fails either one of those, it's definitely not a subspace. If it passes both of those, it doesn't make it a subspace. It only goes one way. So the tests are ways of quickly filtering out things that have no hope of being a subspace. Then if you're not sure, you know, it passes the obvious test, then you would want to proceed to see if maybe you could prove that it is a subspace. So let's think of one more here. Capital Y. This is going to be the set of, well, how about the one I just had? T, 3t, 7t, where t is any real number. Now, I got rid of that restriction before that kept the negatives out. I'm not saying they have to be non-negative. Certainly has the zero vector in there, set t equal to 0. And if I set t equal to anything, I could set t to that negative of that, and I'd have the negative of that vector. So it's passing all the easy tests. Looks like maybe it's a subspace, is it? Well, the way to prove it is, and the answer is yes, this is a subspace. What you want to show is that it's closed under addition, vector addition, and it's closed under scalar multiplication. Okay, so the way you would prove that is you would just choose two vectors at random from Y. Let's say V and U be in Y, cap Y. Then V is equal to, well, you gotta be able to make a choice for T that gives you the V vector. Maybe that one is, say, A, 3A, 7A, for some real number A. And likewise, U is going to be B, 3B, 7B for some real number B. So what happens if you add them up? Well, when we add these, we get A plus B, comma, 3A plus 3B, 3A plus 3B, which is 3 times A plus B, and 7 times A plus B. And that's equal to, if you really wanted to spell things out, T, 3T, 7T, where T equals A plus B. So U plus V is back in cap Y. Therefore, Y is closed under vector addition. And then you do the same thing for scalar multiplication. Let K be a scalar. V be in cap Y. Then V equals A, 3A, 7A for some A. KV is equal to KA, 3KA, 7KA equals T, 3T, 7T for T equal KA. Therefore, Y is closed under vector addition. Whoops, not vector addition, scalar multiplication. Well, that's all you have to prove. And I'd write it down except I ran out of space. Therefore, Y is a subspace of R3. Why? It's closed under vector addition and also closed under scalar multiplication. And that forces everything else you need to be true. And there's a long list. If you go back and look at the list of a definition of a vector space, I don't know, it's like 10 different conditions. But if you already are starting in a vector space and you're just looking at a subset, you only need to check these two things to tell whether it's a subspace. Does that do it? Was I talking to Jack?
Yep, that does it.
Okay. Well, I think we're getting near the end here. Linear transformations. The definition of a linear transformation is any function on a vector space that does this. The function of a constant times x plus a constant times y is equal to a times the function of x plus b times the function of y. And you might notice that multiplication on the left by a matrix does that. And as a matter of fact, it turns out that multiplication by a matrix is the only kind of linear transformations there are on Rn. You could specify it in some other fancy way, but you'd also be able to express it as multiplication by a matrix. And if you know what it does on a basis, what the linear transformation does on a basis, you can figure out what it does on any vector at all. And maybe rather than wait for a question, I should just give a quick overview of that. I can give you an example. These are, once you know well, you already knew once. Once I remind you of the trick, you will be able to do these quite quickly. So here's what we know. A linear transformation, if you compute it on, let's make it simple, the standard basis, suppose you get 2, 3, 2. If you take the same linear transformation on the second basis vector in the standard ordered basis, you get 1, 1, 1. And let's suppose you are told that on the third standard basis vector, you get 0. I'm just making this, you should get the impression this is random. It is. I'm just picking things that are simple and that occur to me. So how do we compute this same linear transformation on, say, 5, 7, 14? Well, what you do is you say this. We know that every single linear transformation on Rn can be written as a matrix multiplication. And what we know is that if you apply this vector, I'm writing lightly because I'm going to want to change this in just a minute, 1, 0, 0, then the product has to be 2, 3, 2. Well, the only way that could possibly be is if 2, 3, 2 is the first column of this matrix. Similarly, if I replace that by a 0 and put a 1 on here, well, then I've got to get 1, 1, 1 popping out. And the only way that could be is if the second column is 1, 1, 1. And then finally, if I put that back to 0 and make this a 1, then I get 0. Well, it must be the third column is that. So these are the images of L on the standard basis vectors, 1, 0, 1, 0, and 0, 0, 1. So L of V is nothing other than 2, 3, 2, 1, 1, 1, 0, 0, 0 times V. That's it. We have unpacked it. Now, if you were given 3 other vectors, which form a basis, then you would know how to do this in that non-standard basis. And then if you want to know how to do the calculation with respect to the standard basis, you use the tricks that we had before. You draw your picture. I've got a non-standard basis A and B. S is always around. To get up here, I multiply by A. To get down here, I multiply by A inverse. And to go from here to here, it's A on the left and then B inverse on the left. Whoops, like so. B inverse on the left. And to go, that's in this direction. And in this direction, it's B on the left, followed by A inverse. So you simply, you start with a standard X, you translate it to the new basis, and then you multiply by the basis by the matrix that's obvious. So that's sort of talking at the 10,000 foot flyover. Let me give you a specific one. Suppose we know that the linear transformation we have in mind, if you multiply by, if you feed 1, 1, 0 into it, you get 2, 6, 1. If you feed 0, 1, 1 into it, you get a string of 1s. And I better save some space here. If you feed, which one did I miss? 0 in the middle. You get, I don't know, 2, 1, 3. Okay, So that means I actually know what this linear, excuse me, I know what this linear transformation is relative to this weird basis here. Let's call it basis B. So relative to basis B, if you write your vector with basis B coordinates, what you're going to have is 261, 111, 213 times the coordinates of X relative to B. The question is, how would you do this? Suppose I have the coordinates of X relative to the standard basis. Well, the answer is, you're still going to work with this matrix. But we have to convert these coordinates to basis B coordinates. So if you know the coordinates in the standard basis up here, how do you get them in B? The answer is you multiply by B inverse. So you multiply by B inverse, and B inverse now are these basis vectors. 110, I gave the second one here, 0, 0, 1, and then the third one, 101, compute the inverse, and then start with standard basis vectors. This product right here is the matrix of your linear transformation. But what it's doing is this. It's starting with standard coordinates. That inverse is converting to base B coordinates. Once you have the base B coordinates, then you multiply by the base B matrix, and poof, you've got the image of the linear transformation. So that's an explanation fast enough to guarantee either to remind you if you already knew, or to convince you, oh, I better go back and look, if you didn't remember. But I don't have time for much more than that tonight, so. Okay, so that's that last big item that I would expect someone to ask me about. Other items on this page, Kramer's rule, determinant of a product of matrices. If you have square matrices, all of the same size, say ABC, the determinant of the product ABC is the determinant of A times the determinant of B times the determinant of C. Works great for products. Fails miserably for addition. The determinant of A plus B plus C is not the determinant of A plus the determinant of B plus the determinant of C, except in special cases. Anybody want to ask about any of that? Only other things on here that I would see likely that someone would have questions on, that I'm personally anticipating, let me put it that way, would be occasionally I see people have trouble with writing solutions to systems of equations in parametric and vector form. And sometimes people are a little vague at this point in the course on what the null space and the column space of a matrix are. Does anybody want to ask about either one of those? Or some other thing here that occurs to you is fine too. Okay. Fortunately, we've been talking about some related ideas already. Let me stop the share here. So I'd love to give you a general explanation, but what will happen is it will be impossible to follow in a short order. So I'm gonna write down something specific here. And I will make this a non-invertible matrix because I want it to be something interesting. Okay, turns out that's not invertible. What I did is I took the second column minus the first column, and I think, yeah, I got the third column. Okay, now the column space of A is the span of the column vectors. Another way of thinking about that is this. It's all the vectors y that we can construct this way. Let me give this a name. A times some x, all these. That's the column space. Anything you can reach by multiplying A on the right by a vector x. That's the column space. The null space is all the vectors x that have this property, A times x is the zero vector. And these two things are tightly connected. They're connected in this way. The dimension of the column space plus the dimension of the null space always adds up to the number of columns. In this particular case, you have two linearly independent columns. So the dimension of the column space of A is 2. You have one linearly independent vector in the null space of A. Therefore, dimension of the null space of A is 1. And when you add those up, you get 3. Now, I could say more about this. What is the null space? It is the span of this single vector right here. What I know is I got this by taking 1 times this and minus 1 times that is, whoops, 1 times this times minus 1 times this is guaranteed to add up to this. So if I put a minus 1 on this, then I would get the first column out of that sum, and I get the negative of the first column out of that sum. So that tells me that this vector right here, minus 1, 1, minus 1, is in the null space. And that's the only thing in the null space. It's the only way you can get a 0. Now, of course, you could change these all to 2's, or you could change the sign on all of them, but nevertheless, they have to be those proportions. So the span, let me go ahead and change the sign on it, but I get fewer negatives. The span of that, 1 minus 1, 1, is the null space of A. And the span of, say, the first 2 columns, actually you could take any 2 columns, it would work. Is the column space of A. So there's the null space, there's the column space. Here's the fact about their dimensions. When you add them up, you get the number of columns. So was there something else I was going to tell you about that? Or just in general? I think it was just generalities, right? Oh, row space. It's what you think. It's the span of the row vectors. Now you could write them vertically if you want, or not, doesn't matter. The first row is 1, 3, 2. The second row is 2, 3, 1. The third row is 0, 2, 2. So there's the row space. And there is a concept sort of like a row null space, but what it is, it's the null space of A transpose. And the dimension of this plus the dimension of this always adds up to the number of rows. Now, it's really easy. And the rank of A is equal to the dimension of the column space. That's the meaning of rank. And it's also equal to the dimension of the row space. That's actually kind of not such an easy proof. But the column space and row space always have the same dimension. They need not be equal, but they have to have the same dimension. So that's the rank of a matrix. You can find out the rank of a matrix in multiple ways. Number one, if you are working with MATLAB, you type in the matrix and then you type in rank A and it tells you. Okay, that's a pretty good way. But another way is you look at the row reduced echelon form and you count the number of non-zero rows. That's the rank. So if you row reduce this matrix here, you'd get 2 rows that are not all zeros and 1 row that is all zeros. So its rank is 2. You can do the same with its transpose. And if you take the transpose first and then you take the row reduced echelon form, you will find out you have 2 non-zero rows. The value of that is that if I started with A and we had it here in front of us, I'm thinking of something concrete. If I wanted a basis for, I've run out of room, the column space of A, what I do is I take the RREF of A transpose. So now I'm changing the columns to rows. Take the RREF, the non-zero rows are a basis of the column space of A. How do I get a basis for the row space of A? Well, same way, except you don't need the transpose. You're already the things you want to study are already rows, so you don't have to take the transpose. Take the RREF of A, non-zero rows of that RREF are a basis of the row space of A. And how do you get the null space? These are standard final exam questions. That's why I'm going through them. How do you get the null space of A? A basis of the null space of A? Well, you start with A. You ask what vectors would produce that product. Well, that's the same as solving this system of equations. And so you get the RREF of A, only you can think of it as having an extra 0 vector there. You can put it there or not, it doesn't matter. And then you read the solution. So it's the same process to get there, but you interpret different. If you want a basis of the null space, I didn't write basis here. You row reduce A, and then you read off the solution as if you were solving a system of equations, because indeed you were. We're solving that. If you're looking for, say, a basis of the row space, you compute RREF all over again, or just once, and then just copy the non-zero rows. That's a basis for the row space. Okay. So if you know the tricks, those questions are really short. You basically, you type them in your calculator, either transpose or not, take the RREF, and then interpret in the proper way. And you got your answer right away. And that's what's intended on a question like that. You know, you don't have to wax eloquent. You just, I did this. Here's what I got. And you're done. I think we're about there. You know, there's no end of things I might suggest, but unless there are other questions, I think that's a good place to end. I'm looking at my chat box here. I don't see any new questions there. So, sounds like we're done for the night. I'll see you on Tuesday then. Don't forget to make up your formula sheets. And I wish you well. Let me say, by the way, I really have enjoyed teaching this class. I've enjoyed being with all of you. I've gotten the opportunity to know some of you a little bit more since you're here in person, and others, of course, just little bits and pieces from our interactions online and in the few times that you come to class. But it's been a good semester for me, and I've enjoyed being with you all, and I consider it a privilege to be able to teach you. Some of you are probably smarter than me, and you know, you're going to go on and do great things. And I got one little drop in the bucket of your preparation, and that's great. Okay, I will see you. I'll see you on Tuesday.